Assalamualaikum warahmatullahi wabarakatuh. My name is Ain Hannani Binti Rahman. My student ID is 20224960004. I am from CEEH 2203B, and today I would like to talk about the experiment 4, which is the Osbourn-Renault experiment. The abstract of this experiment is that the experiment was carried out by using a device known as Osbourn-Renault's demonstration, which has a model Soltec FM11. In Osbourn-Renault's experiment, laminar, transitional, and turbulent flow are observed while the Renault's number is calculated using a procedure that yields a dimensionless number such as Renault's number. The experiment begins by injecting blue dye into the glass tube. This is to ensure that the flow is visible to be seen by the observer. This was accomplished by controlling the water flow via the inlet and exit valve until the dye line for laminar, transitional, and turbulent flow was reached for each wanted condition. The volumetric technique was used to measure the flow rate, and the measurement duration was established at about less than 10 seconds. The introduction of this experiment. Who is Osbourn-Renault? He is the first person to create the Renault's number. Osbourn-Renault is his name. He was an English scientist and an engineer who is most known for his contribution to hydraulic and hydrodynamics. His legacy lives on in the Renault's number, which serves as a standard dynamic similarity and therefore accurate modeling in several fluid flow experiments. Now, what is Osbourn-Renault experiment is about? The Osbourn-Renault experiment was carried out to identify laminar, transient, and turbulent flow. By restricting the velocity, such transient from laminar to turbulent may be immediately witnessed. From the blue ink is combined with the contrast media injection to create a laminar or turbulent display in the streamline. The flow are plainly visible. The outcome was then utilized, accounting for each measurement to calculate the Renault's number. The objective of this experiment is first to obtain three flows, which are laminar, turbulent, and transitional flow. The second objective of this experiment is to calculate the Renault's number to determine the type of flow. The theory of this experiment is that different kind of flow have different value of Renault's number. If the Renault's number is less than 2100, the flow is laminar, showing a constant line of streamline. If the Renault's number is in between 2100 and 4000, the flow is transitional, showing a great fluctuation in flow. If the Renault's number is more than 4000, the flow is known to be a turbulent flow, showing a fluctuation in a flow. Now, how to calculate a Renault's number? Taking the Renault's number equals to U times L over mu, where U is the fluid velocity, meter per second, L is the length of the glass tube in meter, and mu is the kinematic viscosity, meter square per second. This is the apparatus used in the Osbourn-Renault experiment, which is also known as Osbourn-Renault Demonstration Equipment Model Soltec FM11, provided by UiTM Shah Alam Faculty of Chemical Engineering. The procedure of this experiment is that firstly, the equipment was set up by ensuring the inflow valve and the overflow valve are open, whereas the control valve is fully closed before the pump are turned on. Next, the experiment on laminar flow was started by partially opening the outflow valve. The pump is switched on, and the experiment will begin by slowly opening the control valve to begin letting the water into the head tank until the water level is constant and stable above the overflow pipe. The experiment was started by injecting dye into the equipment's glass pipe and out the outflow pipe. The flow is observed and recorded. Next, the flow rate is measured by the volume obtained within 10 seconds. From the flow rate obtained, we were able to calculate the Renault's number. The reading and the calculation are repeated 3 times. The experiment is continued by observing transitional and turbulent flow by repeating step 3 to step 5 to different flow rates by controlling the outflow valve. The flow of state is confirmed by the calculation of Renault's number. Finally, the equipment was shut down accordingly by removing the water from system, and the system is switched off. This is the result obtained from the experiment conducted. The calculation of this experiment is started by noting that the volume of laminar and transitional flow is 90 milliliter, which is also equivalent to 0.09 liter. The volume of turbulent flow is equal to 500 milliliter, which also equivalent to 0.05 liter. The density of water is 1000 kilogram per meter cube. The dynamic viscosity of water is 0.89 times 10 power of negative 6 meters square per second. The diameter of glass tube D is equals to 0.0156 meter, and the area of glass tube A is equals to 1.91 times 10 power of negative 4 meters square. Then it is noted that the fluid velocity V is equals to Q over A, where V is equals to fluid velocity meter per second, Q is the flow rate meter per second square, and A is the area. Next is the Reynolds number, where Reynolds number is equals to Vd over U, where the V is velocity of fluid, D is the diameter of the glass tube, meter, and the U is dynamic viscosity, meter square per second. The calculation is then start for laminar flow. First is to calculate the volumetric flow rate Q, where Q equals to volume over time, where Q equals to 9 times 10 power negative 5 divided by the time, which is the first time recorded for the first observation, which is 8.90 seconds, where Q is equals to 9.86 times 10 power of negative 6 meter cube per second. Then, to calculate the fluid velocity V, where V is equals to volumetric flow rate Q divided by the area, where V is equals to 9.86 times 10 power of negative 6 divided by 1.91 times 10 power of negative 4 meters square. So the V is equal to 0.05162. Lastly, to calculate the Reynolds number, where the Reynolds number is equals to fluid velocity V times with the diameter of glass tube D divided by dynamic viscosity U, where the Reynolds number will equals to 0.05162 times 10 power times 0.0156 divided by 0.89 times 10 power of negative 6. Hence the Reynolds number is equals to 927.779, which shows that the Reynolds number is less than 2100, and it shows that it is a laminar flow. The next two trial for laminar flow calculation is repeated using the same technique and formula. Next, the first trial for calculation transitional flow is started by calculating the volumetric flow rate Q, where Q is equals to volume over time, where Q is equals to 9 times 10 power of negative 5 divided by 3.40, where Q is equals to 2.65 times 10 power of negative 5 meter cube per second. Then to calculate the fluid velocity V, where V is equals to volumetric flow rate Q divided by the area, V is equals to 2.65 times 10 power of negative 5 divided by 1.91 times 10 power of negative 4, hence V is equals to 0.1386 meter per second. Lastly, to calculate the Reynolds number is equals to fluid velocity V times with the diameter glass tube D divided dynamic viscosity U, where the Reynolds number is equals to 0.1386 times 0.0156 divided by 0.89 times 10 power of negative 6. Hence the Reynolds number is equals to 2431 times 91. This shows that the value of Reynolds number for transitional flow is in between 2100 and 4000. Then the next two trial for transitional flow is calculated using the same method and technique. Last but not least is the calculation for turbulent flow for the first trial. Is to calculate the volumetric flow rate Q, where Q is equals to volume over time, where Q is equal to 5 times 10 power of negative 4 divided by 7.37, and Q will equals to 6.78 times 10 power of negative 5 meter cube per second. Then to calculate the fluid velocity V, where V is equals to volumetric flow rate Q divided by the area A, V is equals to 6.78 times 10 power of negative 5 meter cube per second divided by 1.91 times 10 power of negative 4, then V will have an answer of 0.3550 meter per second. Lastly, to calculate the Reynolds number, taking the Reynolds number equals to fluid velocity V times with the diameter glass tube D divided by dynamic viscosity U, where the Reynolds number equals to 0.3550 times 0.0156 divided by 0.89 times 10 power of negative 6, Reynolds number will equals to 6222.01. This shows that for the turbulent flow calculation, the Reynolds number is more than 4000. Then for the next two trial for turbulent flow calculation is repeated by using the same method and formula. The discussion for Osbourn-Renault experiment is that this experiment yielded successful result as the stated objective were achieved. Specifically, the experiment involved the determination of three distinct types of fluid flow, namely laminar, turbulent, and transitional flow by the calculation of Reynolds number. The type of flow can be identified by calculating the Reynolds number. The purpose of the Osbourn-Reynolds number experiment is to study a particular feature of the fluid in the pipeline. It is known that there are three different types of flow to occur, which are laminar, transitional, and turbulent. The nature of flow along the pipeline was determined by observing them. In this experiment, Reynolds number is the medium that shows and distinguishes the characteristic of laminar, transition, and turbulent flow. The parameter that is being considered in this experiment is the fluid velocity, density, viscosity, and the length of the glass tube. In this experiment, it was studied that the Reynolds number relates closely to the flow pattern of the fluid. The lower the Reynolds number shows that it is laminar or streamlined flow, while a moderate Reynolds number shows a transitional flow where the flow is not as streamlined but not as vigorously fluctuated. Lastly, a very high Reynolds number shall be concluded to be a turbulent flow where the flow of fluid can be said to be chaotic and irregular in motion. This experiment was a success as all three of the flow pattern was seen in the experiment conducted. This is where laminar flow has Reynolds number of less than 2100, at which were 927.776, 904.850, and 907.606, whereas transitional flow has Reynolds number between 2100 and 4000, which were 2431.31, 2349.91, and 2431.31. Lastly, turbulent flow in this experiment verified that it has Reynolds number that are more than 4000, which were 6222.01, 0647.65, and 5974.23. Hence, overall, this experiment was a success splendidly and confirmed that Reynolds' statement as well as achieved all the objectives needed in this experiment. The conclusion for this experiment is that in conclusion, this experiment has provided an observed demonstration of the underlying principle that regulates the dynamic of fluids. The experiment reveals the existence of three distinct forms of flow, namely turbulent flow, laminar flow, and transitional flow. The experiment has exhibited how Reynolds number play a prime role in defining the flow region and how the interaction between viscous forces and inertia affects the fluid behavior. In this experiment, it is observed that laminar flow exhibits a constant and gradual movement at a fixed velocity, while turbulent flow demonstrates rapid and vigorous motion. In a pipe, the movement is transitional flow shift between laminar and turbulent. When the water flow rate is increased as the blue dye continues to travel at the same speed in a straight line, the data obtained using the Reynolds number calculation indicates that the laminar flow is occurring between it is less than 2100. It is a transitional flow because a Reynolds number is between 2100 and 4000, and the blue dye travels at a consistent speed before accelerating suddenly. Last but not least, when there is a significant increase in the flow rate, the blue dye travels in an unpredictable and rapid manner. When the Reynolds number is used, the resulting value will be greater than 4000, which indicates that the flow is turbulent. It can be seen that the Reynolds number equation does not have any dimensions due to the fact that there are no units left over after the computation. The recommendation for this experiment is that parallax error may arise from the experimenter's eye location during the water volume measurement at the conclusion of each set. The eye level should be perpendicular to the readings on the measuring cylinder to avoid parallax error, which might distort the experiment's result. Apart from that, a picture can be taken since it is more systematic and has a higher chance of accuracy since the observer can adjust the height of their hand to be parallel to the reading of the experiment. An adequate, stable location should be chosen for the experiment in order to get a clearer picture of the flow line, not Thirdly, that a white clear paper should be placed at the back of the glass pipe when the ink has been injected to observe and to identify clearly the type of flow, whether it is satisfies the characteristic of each flow types, laminar, turbulent, and transitional flow. Last but not least, before performing the experiment, the instruction should be carefully read so that everything goes according to plan and that mistakes would not cause time to drag and squander for a better, easy, and effective execution and result for this experiment. Thank you very much.